Assalamualaikum and a very good morning. So my name is Tarmizi bin Ahmad Yuzdim. I am from the University Technical Malaysia Melaka, and today I'll be presenting on my research work entitled Zero Short Power Consumption Forecasting for Electrical Motor Driven Compressors using a time series foundational model. So this is presented to 2026-16 IEEE Symposium on Computer Application and Industrial Electronics. So the introduction: compressors are vital for liquefied natural gas regasification terminal, but it consumes massive amount of power. Typically, for predicting the power consumption, the traditional methods relies on models such as the long short-term memory and convolutional one dimension, which requires extensive site-specific training and large dataset, and these often are unavailable or costly in industrial settings. So in our research, we would like to investigate the usage of a time series foundational model, specifically the Google's time series foundational model, which enable us for zero shot forecasting of the energy consumption. This is with the hypothesis that the prediction won't be requiring any task specific training. Hence, it will be much more cheaper than using the standard LSTM or conventional one dimension. So the proposed model we are using for this research work is the Google's Times FM, Times Foundational Model. This is available at the Google GitHub repository. So the time series foundation model is a pre-trained time series foundation model, meaning that it is pre-trained with a large amount of data, with large amount of time series data. The architecture is a decoder-only transformer-based model developed by Google Research. The key principle in this model is segments data into patches for training efficiency. It was pre-trained on vast diverse dataset to enable generalization across many domains, not only on the energy prediction domain, but this can be capable to be applied on many time series prediction domain. So it supports univariate forecasting with a context length up to 512 time points. So our case study is a liquefied natural gas terminal in Melaka, Sungai Udang. The facility layout consists of multiple compressors. We have compressors that are handling the vaporized gas from storage, and we have the compressors that are handling the final feed the final pipeline network. Compressors that are connected to the gas storage are the boil off gas compressors, in which here we highlight as BOG-A, BOG-B and BOG-C, and the RGTech compressors, which handles the feed towards the final pipeline networks, is denoted by this RGTech A and RGTech B. So the data consists of 534 hourly observation per unit. This data was collected over the span of 3 weeks. So the idea in this scenario, we would like to predict the energy consumption of each compressors, the BOG compressors, as well as the RGTech compressors. So our methodology is as follows. So first we set up a baseline, which consists of the long short-term memory model and convolutional one-dimensional model, trained from scratch for each of the compressor mentioned earlier. We perform two types of prediction. The first prediction is the 1 hour ahead prediction. This consists of a context window of 24 hours for prediction windows of 1 hour. Another prediction method is the 2-day ahead method. This consists of a context window of around 188 hours with a horizon prediction window of 24 hours. So in all scenario, we enable positivity constraint and use 80% of the prediction interval for uncertainty. So these slides highlight the stability analysis of the proposed method. So for consistency, we test across 5 distinct temporal split. We have split 1, split 2, split 3, split 4, split 5. And our findings shows that the application of times FM showed a high stability in the Argitect compressors. If you can see here, the variance between the Argitect compressors and the BOG compressors is different, where it shows here that the Argitect compressors are more stable when compared to BOG compressors. A spike in BOGA was identified as a known nonlinear process shift rather than model instability. Okay, this is our results of the prediction, starting from the long horizon day ahead prediction. We can see that comparing our proposed method, performing zero shot prediction times FM, perform much better in many of the compressors. You can see here for BOGA, for example, we obtain the lowest RMSE for the 1 hour forecasting window and 24 hours forecasting window, with the mean absolute error of 0.92% and 1.27%. Similarly, we can see that for Argitect A and Argitect B, both of them perform much more better when compared with convolutional one dimension and long short-term memory model. You can see here that if we were to focus around the 24 hours prediction horizon window with a 168 hours context length in Argitect A and Argitect B, the times FM model outperform all of the other models, including convolutional one dimension. For short horizon prediction window, we found out that the times FM achieved the best result for boil of BOGA or boil of gas compressor A. For Argitect units, convolutional one dimension remained highly competitive, but times FM still provide realistic performance that surpass the LSTM model. But the advantage that we would like to highlight over here is that using the times FM model, we are performing the prediction in a zero-shot manner. So unlike the use of LSTM or convolutional one dimension, in which we require the training of the model, this time we would like to highlight that the usage of times FM doesn't require us to train the model. This is being performed in a zero-shot manner. Although we don't fine-tune it or do any training on the dataset, we can still see that the result, the performance of the model is highly competitive when compared to the convolutional one dimension and LSTM model, which are typically used for time prediction scenario. Another thing that we would like to highlight is the impact of contact lengths. The discovery is that increasing the history from 24 hours to 168 hours contact length dramatically reduces the error. For example, Architect A, we obtained a 71.3% improvement for 1 hour horizon, and Architect B, we obtained a 75.3 improvement for the 24 hours horizon. So the conclusion that we would like to highlight over here is that prolonged historical context, meaning the bigger the context length or the context window for prediction, is essential for foundational model stability in this kind of industrial tasks. So the conclusion for our study is that Times FM is an exceptional plug-and-play solution for long-range industrial forecasting. This leads to data efficiency, negates the need for site-specific retraining, making it ideal for data-scarce environment. So in the future, we would like to investigate the multivariate extension and fine-tuning strategies to enhance the robustness of this model. So thank you very much for listening to my presentation.